Hello students, today we are going to find the electrostatic field due to a charged earth, uniformly charged earth. Okay, so the uniformly charged earth is shown in the figure that is given by ABC. Okay, so it is uniformly charged earth, it is uniformly charged. So what is the meaning of the statement of uniformly charged earth? That means the uniform means the line charge density. The line charge density lambda in the arc is constant. That means the dq/dl, if the dl is the a small line element here, and the charge in the dl is dq, so dq/dl is constant, and which is called lambda. Okay, so we have to find the electric field at the center of the arc. Okay, uh, due to the whole arc. Okay, so fully charged arc. So what we have done, we have to do first is we have to draw a line. So this small line element is taken at an angle theta, and this small line element subtends the angle d theta at the center. So I have taken in this direction, that is a horizontal, that is x-axis here. Okay. So that is our first task. So we have taken the radius as r. So dl, according to the geometry, it becomes r d theta. So the dq, the charge, is equal to lambda into dl, which is lambda r d theta. Good. We have found the charge on the arc. We have drawn the line, we have drawn the radius to show that the dl subtends d theta at the center of the arc. Good. That means that's at the center of the circle whose arc is this ABC. So again, I'm going to bring the picture below so that I can take the components of the electric field to make you understand what is the further calculation. Okay. So let me start from here. So here, to get the electric field, generally we place a +1 charge where the electric field is to be found. So dl, since we have taken the positive charge density here, so dq will repel this electric field in this direction, and which is said to be, yeah, so, and which is whose components are, so that is a dE. Okay. So I have taken here two directions, perpendicular directions, so that I can decompose the electric field into two parts. One is, yeah, so one is along negative y-axis, which is negative y, and it is along negative x-axis. Since it is theta in its vertically opposite angle, it is also theta. So this is dE cos theta, and this is dE sin theta. Okay. So the vectorially we can write the dE as, very easy to write. So dE cos theta and dE sin theta. So vectorially we can write that so dE cos theta minus I cap, because it is opposite to the x-axis, positive x-axis, and dE sin theta opposite to the j-axis, sorry, y-axis, is minus j cap. So this is our electric field. Good. And dE, we know dE. dE is simple k Coulomb constant, k dq by r square. And dq we have already written, right, in the previous page. So I'm going to write the dq here again to remind you that what is dq is. So that is lambda dl and lambda r d theta. So now our task is to integrate that to get the electric field. So the total electric field we can found the integration of that. It is minus dE cos theta I cap plus dE sin theta j cap. And I'm going to take the common outside because it is a common factor. So that is cos theta I cap plus sin theta j cap. And writing the expression of the d explicitly, I'm putting the dq even here. So that is lambda r d theta. So I'm skipping one step. I put d equal to k dq by r square, and in the place of dq, I have used the its explicit expression. So that becomes this. So cos theta I cap plus sin theta j cap. Fantastic. So we have to integrate at everywhere. So that is the integration, and uh, here d theta. Yes. So one power will be gone of the R, and K lambda R are common, so they are taken outside of the integration. So integration is now cos I cap plus sin theta j cap. And the limits of the integration must be, so it is starting from the zero because the theta is taken the angle with the x-axis. So it is starting from the 0 to the value of theta, so 0 to theta. So the electric field becomes, we now use so the integration of cos theta is sin theta. Its upper limit is theta, lower limit is 0 into I cap, plus the integration of sin theta is minus cos theta. Its upper limit is theta and lower limit is 0 into j cap. So that is k lambda by r, that is sin theta. And in the lower limit that is 0, sin 0 is 0, so that is sin theta I cap. And here it is very, very easy to see that is a cos theta minus cos theta and cos theta minus cos 0 j cap. And cos 0 j cap is simple sin theta I cap. And cos 0 is 1, so it becomes cos theta minus 1 into j cap. So it can be written as kr I cap sin theta. So that is it can be written as 1 minus cos theta j cap. So it is a vector expression of the E, okay, due to the arc at the center. Okay. So this can be simplified more like this. So I can write that. So it is R, say. So I can write I sin theta as 2 sin theta by 2 cos theta by 2. And it is 1 minus cos theta can be written as 2 sin square theta by 2 j cap. So that is, it becomes k lambda by r. I'm taking 2 sin theta by 2 outside. So it becomes I cap cos theta by 2 plus j cap sin theta by 2. So ultimately it becomes 2 kr by lambda sin theta by 2 into I cap cos theta by 2 plus j cap sin theta by 2. So that is the expression of the E at the center when it is taken to be a circular arc. Good. Good. So yeah. So let us do this the further things. So for example, if I will be given or will be given the arc which is making an angle 90 degree, that is 1/4 of the circle. That means this angle, the theta becomes 90 degree. So E becomes, that is 2k lambda by r. Okay. So I'm just putting all the things there. So it becomes sine 45 degree plus I cap sine cos 45 sine 45. Both are same. So I cap plus j cap. So again I'm writing is 1 by root 2. So it becomes k lambda by r I cap plus j cap. Because sine 45 degree is 1 by root 2. 1 by root 2 into 1 by root 2 is half. And one these two factor will be gone. So this becomes electric field. Okay. Okay. So this is the expression of the electric field at the center of this, and its direction can be found from here. The magnitude of the electric field. So I have taken here a special case. I have to write the special case. So there is a special case. The special case is it is say when the theta is pi by 2. So this is the electric field when the charge is a positively charged arc is taken, and this is y-axis and this is x-axis. Okay. So for this case, the electric field actually pointing towards around the 45 degree, which is appearing from here because all the angles are 45 degrees there. So there is a resultant electric field in this direction, say, that is E. So this is making 45 degree with x-axis and y-axis, and this is the value of the electric field here. Okay. For any arc having theta that we have already found here. So if I take the magnitude, so the magnitude of the electric field, the magnitude of the electric field of the electrostatic field, whether I should write electrostatic field because there is a big difference between electric field and electrostatic field. So I have to write electrostatic field for any arc, okay, subtending angle theta is given by the magnitude of this one. So it is the magnitude of E. Okay, so the bracket is this magnitude. We know the this magnitude E. Okay, so this is the magnitude is 1, and the rest thing is simple 2k lambda sine theta by 2 by r. Okay, so yes, so we can check the magnitude. So if I consider the full circle, okay, if I consider the full circle, the theta, the whole theta, this total full theta becomes this is 2 pi, and the total electric field must be zero because the electric field from the upper side is cancelled by the lower side, right? So the electric field from the upper semicircle is pointing downward, and from the lower semicircle is pointing upward with the same magnitude. So it becomes, so they will cancel each other and it becomes zero. So it is pretty evident from this expression too. So if I put here the theta equal to 2 pi, so the value, so it becomes 2k lambda sine pi by r, and that is 0 because sine pi is 0. So the electric field at the center is 0. Even you can move to see the electric field for the semicircular arc, only for the semicircular arc, where the theta becomes pi. So at this case, so we can write to the electric field, the magnitude of the electric field becomes very well known fact. So it becomes 2k lambda by r. So sine pi by 2, it becomes sine pi by 2, and sine pi by 2 is 1. So it becomes 2k lambda by r. So it is a electrical and it is pointing downward. How can I know that is a pointing downward? So we can write the electrical expression. So if I put the all the value pi, theta equal to pi in the expression of the vectorial form, in the vectorial say that is 2k lambda by r sine theta by 2 cos theta by 2 I cap plus sine theta by 2 j cap. That was the expression we have derived. So if I put here the theta, right? So sine, we have put here the expression. The expression is telling me this theta is now pi, so that is sine pi by 2 cos pi by 2 I cap plus sine pi by 2 j cap. So cos pi by 2 I cap is 0 because cos pi by 2 itself is 0. So sine pi by 2 is 1 and that is also 1. So it becomes minus 2 lambda by r into j cap. So it is pointing vertically downward. Okay. So it is now it is so here for semicircular it is the resultant electric field is vertically downward. So we have first of all, so summary, we have already found the expression of the electric field for any circular arc. That is most important. So that is 2k lambda sine theta by 2 cos theta by 2 I cap plus sine theta by 2 j cap. This is the expression we know. We have found that. And we can find the electric for any type of arc with this from this expression. So there is a general expression you can tell. Yeah, good. Next we are going to find another. We have to solve another problem. So it is the electric field, electrostatic field rather, on the axis of the of a charged ring or charged loop. So I am taking this is the charged ring, say, and I've taken that is the positively charged ring, and this is the axis, its axis, and we have to find the electric field at any point P, and which is kept at a distance, say, x from the center of the loop, and the radius of the loop is r. So again, I am going to take a particular line element that is dl, say here, and the line charge density. So it is uniformly charged distribution. Again, I have considered so uniformly charged distribution. So uniformly charged distribution means lambda equal to constant, right? So and like in the previous example, the dq is lambda dl. So that, and to get the electric field at the point P, in our mind, I have to keep here a test charge. So the dq will repel the test charge in this direction. Okay. And I have taken a diametrically opposite line element here, which will with the same charge dq, and it will actually repel this plus one charge in this direction with the same magnitude. Why I am telling the same magnitude? Because the distance from the dl to the point P from both line elements is L. Okay. And we know the magnitude is given by dE, that is k dq by L square. So these are same for both cases. So both electric fields are same. But since the directions are opposite, not opposite, their directions are different. So I have taken this electric field is E1, dE1, and that is dE2. And I am taking, so if this angle is theta, this angle is also theta. So this is theta and this is theta 2, because they are all vertically opposite angles. And I'm taking their components. So I'm taking in this direction. So that is in this direction, that is y-axis, say, and this is in this direction, that is negative y-axis. So here dE2 sine theta, here dE1 sine theta, and along this x-axis, the components are dE1 cos theta, dE2 cos theta, right? So, so here the total components is dE1 plus dE2 cos theta. Okay. Okay. So you can easily see that along the y-axis dE sine, so dE sine theta, dE1 sine theta is opposite to dE2 sine theta, and both, so but dE1 equal to dE2, that means along y the total electric field, that is dE, I should write resultant electric field along y, dEy equal to 0, because they will cancel each other, because their magnitudes are same, because and they are opposite to uh, each other. So that's why their total magnitude is 0. On the other hand, along the x-axis, the total electric field, total electrostatic field is simple. That is dE1 plus dE2. They are being added up right now into sine theta, into cos theta. Yeah. And since dE1 equal to dE2 and that is equal to dE, say, so that is 2 dE cos theta. So only we are, so that is the only electric field component which is being survived in this calculation. So that means it is telling that when a charge ring we are consider uniformly charged ring, positively charged ring, so the electric field at any point on the axis is along the axis in this direction. Okay, so we are now decided. So that is the only one electric field here, only one directions electric field along the x-axis, along the axis. So conclusion is, big conclusion. Conclusion is the electric field along the axis of the ring exist only. Now we are going to find the value of the electric field. So we have to integrate that. So total electric field, the integration due to the, so 2 cos theta is the common, 2 cos theta is constant outside the integration. So integration is over dE say, and 2 cos theta is taken out. So and dE I am writing k dq by L square. So this is say dq, and this was L. And next line is k and L square is common from, because these k is common, it is a constant factor, and L is the distance which is same for from every line element to this point, right? So k 2k by L square cos theta, all the factors are common, only the integration over dq, and total integration of dq is giving me the total charge of the arc that is taken to be q, say capital Q. So 2kq cos theta by L square. Simple. And our last line is to write the value of the, so this is theta I have taken. So we have to write the cos theta from this small triangle, that is PQR. Okay. Any question from here? So I think there shouldn't be any question, because and one more thing we have to consider, that taking a dq integration is very, very crucial here, in the sense that this this we have already taken a factor 2. This factor 2 is appeared because we have paired up the elements. We have taken pairs, diametrically opposite pairs. That means that when integration is taken, we have taken the dq over the full charge, but we have already taken the paired elements. Okay, that means that this dq actually, the integration here, integration it means is a total charge, but since the 2 is taken already, this factor is taken outside, that counts the pairing of elements. That means we have to modify the dq by q by 2, not that is, so dq here is actually q by 2. So again, I'm going to explain this factor again. Why is it q by 2? Q is a total charge of the ring, because that already we have taken the two factor outside, which counts the pairs. Okay, if I integrate the dq only for the upper semicircle, automatically their charges, the contribution of the charges from lower semicircle are taken, right? Because they are being paired up at each time, at each moment of the integration, right? So that is why it is sufficient to integrate the half of the circle, because the two factor is already taken outside. So that is q by 2. So here is a two factor must be there. So 2 to cancel out. So it becomes kq by L square, and cos theta. So we have to write the cos theta. Cos theta from here is very, very easy to see. That is, the base is x and the hypotenuse is L. So it becomes kqx by L, and L square is already there. So it is L cube. Okay. Okay, good. So next thing is we have to find the right now that is kq by x L2, that is the electric field which is along the x-axis at the point x from the center of the ring. Now we have to express the L in terms of the R and X, one which can be found from very easily. That is again considering the triangle PQR. I'm going to draw it here to make you understand again better, just beside the calculation. So it is P, Q, and R. That is, this is R, the radius. This is X, and this is L. So L is root under R square plus X square. And if I use that, so the equation becomes kqx by r square plus x square to the power 3 by 2. Because the root means it is a power of half. So that means this is the final expression of the electric field at any point x on the x-axis, on the axis of the charged ring, uniformly charged ring, obviously.